There we go. Hello. So I posted a video a few weeks ago on this butchered, modified, whatever you want to call it, bulk tape eraser. It's an old unit I picked up on eBay for 30 quid or something a few years ago, and it used to be much higher than this. In fact, here's the other half of it. That's what it used to look like. And it had an aluminium front panel and then a slot here in the front where you put in an 8-inch or up to an 8-inch reel-to-reel recording tape. And there was like a plunger you press down here, and then that switched on a big electromagnet and wiped the tape. And it's a bit of a shame that I've butchered this thing, but I needed an eraser that would handle larger tapes. I use a lot of 10.5-inch tapes. Plus also be easier to play with an electromagnet if it's all open rather than enclosed in here, to stop you hurting yourself. So I did some modification. I chopped it in half, removed this whole mechanism. All it was literally like a sliding mechanism to allow you to push a tape in and out. It didn't really do anything other than hold the tape in the right place. So let's have a quick look, because the last video I did, it had a plastic top on here, and so you couldn't see the actual magnet. So you can see this huge yoke here. It's hugely heavy. It's over 10 kilos, and it's made of, not sure how well it's showing up on the tape, but it's made up of laminated iron or steel sheet. So there's striations going down here across the whole yoke. It's lots of little plates that have been squished together and glued in place. And you can see here there's this primary coil there. It's wrapped in tape, and then that's been painted in some kind of varnish glue to hold it all together. And this is really more or less half of a transformer, so you can see this as being the yoke of the transformer. Here's the primary coil, and you could wind a secondary on there. And I'm wishing now that I'd not fitted this quite so far back in this housing, because if I'd left myself a bit more room, I could get some really stout cable, really thick cable, or pipe even, my brother-in-law suggested, around there, and have a, like, I don't know, 2, 4, 5 turn secondary, and do some fun, have some fun with very low voltage but very high current. Use it for, you know, melting things. I mean, there is room to get something narrow down there, but I think it'll get too hot. So maybe another day I'll modify it again and bring that magnet or that yoke a little bit forward. So anyway, when you turn it on, all that happens is you're generating a rapidly changing direction, strong magnetic field, and it's an even magnetic field that goes, you know, all the way across here. And so I'll just talk a little bit about what I've done in my butchering / modification. So the coil is being switched by this large relay here, and it's switching both the live and the neutral. You can see these chunky cables coming in and out, and I only needed to switch one of them, but I figured I might as well switch both, because it's such a reactive load, has such a low power factor, that when you break the contact on this, because you've got all that magnetism built up in the iron, you then get I guess it's a reverse EMF, and you get a big spark. And so I figured by spreading the load of the disconnection across the live and the neutral, then maybe I'm, you know, slowing down the damage that arcing is doing to the relay contacts in there. So this is a 240 volt operated relay. The coil here is 240 volts, and everything on here is mains voltage, with the exception of a little temperature indicator I've got here. So the what to tell you about next. Yeah, so since the last video, the modification I've done is put this AC 240 volt fan in it to help try and get a bit of airflow. I haven't since then replaced the lid. So the lid is this sheet of vinyl here. This is the old one, you can see where it was glued on. But I've got another bit here which I've roughed up with a sander. So I'm going to glue that on there. And then we'll see how well the fan keeps the temperature down. So quickly talk about the control of the electromagnet, and then I'll talk about the control of the fan. So the electromagnet is obviously powered or switched by this relay, which I've already talked about. That relay is controlled by this little cheap electronic circuit I've imported from China. It's just a little timer unit. So if I plug the electromagnet in now, or plug the unit in, you hear the fan started. Let me just turn that off. I'm not sure if you can see from the angle you're at. No, you can't, but there's a little LED screen there that says 30 on it, and if I press the switch, that's now powered the electromagnetic magnet on, and it's counting down 25 seconds. And the reason I put the timer in there is because it gets very hot and I didn't want to forget accidentally leave it on and start melting things. It's the time duration on the timer unit is variable. There's a little potentiometer, you can adjust it. I think it does sort of 1 second up to 99 seconds, and then 1 minute up to 99 minutes or something like that. There's a jumper to select between minutes and seconds, but obviously I'm on seconds. So the fan unit, just unplug it from the mains. Fan unit is controlled by this switch here, but there's also a bimetallic, not bimetallic switch. Yeah, it is a bimetallic switch, a little miniature one that's I've glued onto just the other side of this coil here. You can't see it, it's just under there, which is a 45-degree unit. So when it gets to 45 degrees, it switches the fan on automatically, or you can switch it on manually with this little switch there. I'll just plug it in again. Then I've also put a red neon indicator to show you when the fan's on. So what I'll do is put the front panel on again and show you a few little experiments with the electromagnet. So I thought it might be interesting to have a look at the magnetic field, and I thought a way of doing that would be to connect a coil to an oscilloscope. So I got this old Philips scope here, and I made well, actually initially I started off using this inductor here. This is just, you know, an electronics component. It's a fairly chunky inductor, so it's got a core of iron and then lots of copper wound around it, many turns. But I got an interesting shape on the waveform, and I wasn't sure, as in it didn't look like a sine wave. We'll have a look at it in a minute. And I wasn't sure whether that was due to the metal core in the inductor or the metal core of the half transformer, the coil, or a combination of both. So anyway, let's have a look. First of all, this coil, all it is a cork that I just wound about 30 turns of wire on, and then just taped up to stop it all falling apart. So let's turn the magnet on. See, there's a lot of interference here. I worked out it's actually coming off the little timer unit is causing this interference. I don't know why, something to do with the capacitive dropper on it maybe. Anyway, let's turn the electromagnet on. So as I gradually move across, you see the strongest point is right in the middle of this piece of iron here, which I guess is what you'd expect. That's the centre of the coil. And you see something interesting happening there. It looks like the magnet's changing direction, and you see where the peak's changing its position, you know, left and right. Also, that's not, it's got an interesting spiky bit on it. It's not a simple sine wave. It's close to a sine wave, but not quite. As I carry on over here, it gets less and less, a little bit of a bump on this rear part of the armature there. So let's just go back on ourselves. There's the high point. So yeah, not far off a sine wave. Let's turn it off. So now let's have a look at this little inductor here, which has got, as I said, a core, an iron core. Completely different shape, which tells me that the main factor is the core in this little inductor. I need to turn the sensitivity down quite a bit. Many more turns on this. Okay, and of course having the piece of iron, which is a much better, conductor's not the right word, much better medium to support magnetism going through it. That's really not the right terminology, is it? But hey, so look at that shape, isn't that interesting? Really pulling quite hard. And you can see there the shift in direction, I think that's what it is, shift of magnetic pole direction is much clearer with this little inductor. Let's do a slow pass, do it as smoothly as I can. And then the last bit at the back. Put it right on the strongest field. You can see, very spiky indeed. Nothing like a sine wave. Okay, so that's the scope demo. Now I'll do something to give you an idea of the kind of physical force that the electromagnet can pull at. Just going to pause so I can set it up. So I think we can all see how this is going to work. Completely non-scientific, but I've got a pipe wrench hung from the ceiling via a set of scales, so you know, suitcase weighing scale or that kind of thing, and it's zeroed out. So if I turn the magnet on, yeah, it's about 5 kilos, yeah, 4.9 odd kilos. I have had figures as high as about 6.5 kilos when it was just a tiny bit closer. The problem is when I lower it a tiny bit, it very easily gets attracted and slams onto the core itself, which I want to avoid. Let's try it side to side. So there we go, and the end of this is quite warm now. I'd say that was 30 something degrees C, and that heat's come from currents that have been induced in this lump of steel, eddy currents, obviously quite significant because this is a big old bit of metal, so to be able to heat that up to 30 something degrees C is yeah, quite impressive. Right, so I'll let the coil cool down a little bit. It is 43.5 degrees at the moment, so I'll just let it cool down for a few minutes and then we'll have a play with some permanent magnets and a few other things. So it's an AC electromagnet, and because it's AC, the magnetic field is going to alternate north and south with the 50 Hertz mains frequency that we have here in the UK. So if you put a piece of steel or iron, it is attracted both when the electromagnet is north and when it's south, and you get that buzzing because of course the sine wave of the AC mains is going through zero. Zero is in the middle here. So 100 times a second, yes, is going through zero, and that's why you're getting this zzz sound, because it's attracting both when it's a north and when it's a south, but there's no attraction in the middle. So if we take one of these, so these are little neodymium magnets, obviously depending on the orientation of the magnet, the permanent magnet, it's either going to be repelled or attracted by the magnetic field, the electromagnet's magnetic field. So enough talk, let's just throw one in. That was bizarre. And they've both escaped. I wonder how many of these I'm going to lose today. Oh, 2 more escaped. 3. Oh dear, I'm not doing very well here. Put 2 in at a time. Oh, and they separated, that's interesting. Oh, that went flying. Whoa! I'm going to be finding these balls for years. Oh, turned off. What's interesting is you can see where the coil is, obviously around here, and it's all gone grey here, just with metal rubbing off the magnets. I mean, it's not actually neodymium on the outside. Neodymium's actually a little bit toxic. It's I don't know, chrome coated, nickel coated, something like that, probably nickel. Anyway, that's warmed up from 20 degrees to 28 nearly now. And that's going to continue to climb, so I'm just going to take this off. What should we do now? Oh yeah, so just put the old plastic top on. Let me just pick it, actually I'll do that later. Right, so what I got in here is 4 neodymium hard drive magnets from the armatures on hard drives, and this pot you can see is cracked. The ferocity that this thing will kick around, I have actually got safety specs on because it is so violent, and those little ball bearing size or style magnets were pinging off at quite a speed as well. Let's have a look at this one. Yeah. That white is, there was a little bit of paint on the inside of the pot, that's all that is. What else? How about just some standard ball bearings? Yes. There's a light stand just behind the camera, and it's covered in lots of little bits of little neodymium magnets. Right. You see how they're aligning, connecting to each other, I think because the magnetic field, or the permeability, magnetic permeability of the steel is greater than of the air. Not particularly exciting, that one. Just going to pause the video. A bit of bonus footage handheld. I should have done this first time around really with these little neodymium balls. Sorry about the wobbly camera, I'm just hand holding this. I warn you, this is extremely loud. Yeah. I wonder if it's better actually with less overhead lighting. Just let's see whether that's better. Okay, one more. I don't know if you can see, but it won't focus very well on that. Yeah, there's a sort of grey diffuse band over the centre where the coil is. Oh, that was fun. Bye.